What is a dynamical system? They are physical quantities that evolve over time, like the velocity of this airplane or the temperature of a cup of coffee. Simulink is a programming language used for modeling dynamical systems. You can design control systems and do that in the continuous or discrete time domain. To get started, let's try a very basic example, an OR gate. We will first do this in Matlab, as that's probably familiar, and then we will do it in Simulink to see how they compare. So hopefully you have Matlab open. Press new, script, and then let's just do x is equal to true, y is equal to false, and then I'm going to create a variable z in which I want to store this, okay? So z is equal to x or y. And to be able to run this, I first need to store this. So OR gate example. I'm going to call this an OR gate example. And then press the run button. So you see you get a logical OR. Now how would you do this if you had an electrical circuit? Well, you probably have a couple of transistors and an input for each of x and y, and either of them going high would also pull the output high. But what's to note out here is you've got three signals, x, y, and z. This is what it symbolically looks like. Now how would we do this in Simulink? Simulink is a program that is separate from Matlab, but it is invoked from inside of it, and they communicate with each other also. On the top left, press on new and then click on Simulink model. This will take you to the Simulink start page, and you're going to get a bunch of options here. Keep it simple for now. Click on blank model. Alright, so this is a blank model, and this is the canvas on top of which we are going to be doing our programming. So first I want to show you where all of your blocks are. So click on the library browser. So for an example, go to commonly used blocks and you'll see, like say, a constant or a logical operator. Now what is a block? A block is simply a piece of code, and by putting a bunch of blocks together, we are able to create Simulink programs. So let's try and make the OR gate as we had seen earlier. So for the OR gate, right, so we've got two inputs and we've got a logical operator and then we have an output. So for the input, I'm going to use these constant blocks. So click on it and then drag it across. Okay, so now I've got a constant block and I'm just going to call this x, okay? So press shift enter and then type x. These names at the bottom of these blocks, while they need to be unique, they do not have significance in Simulink. You know, because in Matlab, for example, if you have, say, the variable x, well, that's the name of the variable. Out here, it does not actually work like that. This is really just more for us to be able to see it. Okay, and then you can go grab another one, right? Or else you can Control C, Control V, so copy and paste just as you would in any other program. Click, and then I'm just going to call this y. Now, grab a logical operator block from here. Double click, because this is an AND gate. I want an OR gate. So go to the operator. So here you can see different kinds of operators, right? So OR gate. Expand. Now here's how this stuff works. So if I've got a block out here, you can join the arrow, and generally it will only allow you to join arrows where an input is going to an output. For example, this is an output, and output cannot go to an input, right? So an input can go to an output. As we start lining up inputs and outputs, Simulink will give you suggestions. You can click on this and it'll join. Another way to do this is click on the origin block, and this is the destination block. So press your control or command key and click on the destination block. Okay, do that again for this one. Now double click on this and then click true. Another way to do this is you can actually click on the value itself and it should, you see what happened there? Now I want to be able to see this. I want to be able to display this. So let's go find a display. Since a value is originating from here, so this is a source, I need to now go to my sink, so to speak. So go to sinks and you're going to find a display block out here. Again, join the two. Now press run. So you're successfully run. It should show you a value, and as you would expect, since this is true or false, so the output is going to be true, or rather, therefore a 1. The same thing. So just to make sure that we are doing the right thing, do a false out here, and then you can also press a Control T or Command T, and now you get a 0. So here's the summary. This is an OR gate in Matlab as a symbolic circuit and in Simulink. Note that in the Matlab version, we create a variable z to assign the output of x or y. However, in the symbolic version, or say in an electrical circuit, or even in Simulink, we don't create a new variable. It's just a new signal that is created that gets propagated. And that's why I like to think of Simulink as being a signal-based language. We have inputs, we perform an operation on it, and create a new signal. Next, I want to talk about how Simulink runs. So first, let's look at Matlab. With Matlab, Python, or C, all of the statements are executed in sequence. When statement 3 in this case finishes executing, that marks the end of the program. In Simulink, however, all of the code runs repeatedly for a specified period of time. I'll demonstrate this concept with the use of a step function. A step function starts at some initial value and then at a specified time jumps to its final value and stays there. So this is a Matlab function that I wrote to show what a step function is like. The details don't matter too much. I just want to give you the general idea as to how Matlab looks different from Simulink, okay? So you have a time vector out here because there isn't actually a concept of time in Matlab, right? So I need to actually create time, right? So create this idea of time, that goes from 0 to 10 seconds, right? And then I have got an initial value of 0 for my step function, right? And then I've got a for loop to iterate through time, so to speak, right? So I'm iterating through time out here and then create a new value for my step vector, and then I display the data. So let's hit run. And then I get a step at 1 second out here. So the takeaway out here is that Matlab is executing each line out here step by step, right? Until line 23, and then the program finishes execution. Now let's see how we would do this in Simulink. So go to your library browser and in sources, get the step function. Now, two things out here. It so turns out that the step function is so important that Simulink has this available in its library, and then grab a scope and run. Okay, so you see a step at 1 second. Now let's just grab another source, like say a ramp function. Okay, so I have a ramp, right? But let me now show you what happens when we add the two. Then run again. It ramps up as you would expect, and then there is a step, and then it ramps up again, right? I mean, you can also plot these together. Let's just plot them together so you can see this. So with a scope, if you want to have multiple signals going in, you can just right click, hold down, drag a line out, and then as you start taking near the block, an input will automatically populate. Leave your mouse and it will automatically join. Okay, now I'm gonna just, I need to just create some space out here because it's all starting to look a bit messy. Okay, now I'm gonna give these signals some names. Let's just call this my step input. How do you do that? You just double click on a line, on a signal, and then type what you need to. Okay, I'm gonna call this my ramp input. Sum of signals. Okay, run again. If you want to create a legend, you can go to configuration parameters, display, show legend. Okay, so now you can see a legend out here. You got the step input. So the color coding, by the way, is always the same. So after a point in time, you'll realize that you've memorized it. It's yellow, blue, and red, right? And so on and so forth. So I got my step, I got the rate, and then when I add the two, I get, the sum of the two, obviously. Well, here is the big takeaway out here. You see, all of this code is running repeatedly for 10 seconds. You see, that's not how Matlab was operating. In Matlab, we had one line after a line, and all those lines executed once in sequence. But out here, all of the code is running repeatedly for 10 seconds. Okay, now let's try and simulate something more meaningful. So engineers are fueled by coffee. Let's try and simulate that cup of coffee on your table. To create the dynamic model for the temperature of a fluid mass, we need to be concerned about the rate of change of temperature. The rate of change of temperature, dimensionally speaking, is equal to temperature over time. Multiply and divide by energy and rearrange. We get energy over time in the numerator and energy over temperature in the denominator. So what is energy over time? That's power. And energy over temperature is the amount of energy required to change the temperature of this cup of coffee by 1 degree Celsius. So that is its thermal capacity. Thermal capacity is specific heat multiplied by mass. So the rate of change of coffee temperature is equal to the convection coefficient multiplied by the delta in temperature between the room and the coffee itself divided by its capacitance, and therefore T dot is equal to K times T room minus T whole divided by thermal capacitance. First of all, I'm just going to create a comment out here so that I can remember. I just have a record of what it is that I'm trying to do. I'm going to create T dot is equal to convection coefficient. You know what, I'm just going to write K. T room minus T whole divided by thermal capacitance. Okay. Alright. And then I'm going to right click on this. Format background color yellow. It is just so that I just want this to look like a comment, so to speak. Okay. So I first need to calculate the rate of change of temperature. Okay. I'm actually, you know what? I'm going to do a couple of other things here. I'm going to create an initial temperature is equal of 70 degrees Celsius and room temperature of 20 degrees Celsius. Okay, let me just zoom in here so you just scroll with your mouse. Okay, so this is what I'm going to do. This is my governing equation, and here is the initial temperature for the cup of coffee, and here is the room temperature. All right, cool. Okay, so I'm going to start with creating an expression for T dot. On the right hand side, K is a constant, the room temperature is a constant, and the thermal capacitance of the cup of coffee is a constant. So let's create a constant for K. I'm going to give this a value of say 2. We'll create another constant for the room temperature. And that's 20 degrees Celsius. Then I will create another constant for thermal capacitance. Now, how do I calculate this? Well, coffee has got properties similar to water. So I'm going to use the properties of water for this. Let's say this is specific heat, so that's Cp, and this is 4200 joules per kilogram degrees Celsius. Okay, so the volume is about 300 milliliters, which I need in meter cube. So let's just say that 300 E minus 6. So that is scientific notation. And finally, I need density. So if I multiply volume and density, I should get mass. Then I'll create another product block. And this should be capacitance. Okay, now I have got the denominator. I now need to calculate the numerator. However, I do not have an expression for the temperature of coffee yet, because that's basically why we are running this simulation. So I'm going to create a dummy variable for that for the time being. Let's just give this a dummy value of 70. Okay, so now I need to subtract these two. Then multiply. Okay, so that gives me the numerator. Now if I divide these two, I should get an expression for T dot. Okay, now how do I get temperature? Well, this is T dot, so that's the rate of change of coffee temperature. So if I integrate that, I should get the temperature of coffee itself. Okay, so this is T dot, and this right here should be the temperature of coffee itself. So remember when I created a dummy variable for the temperature of coffee? I'm going to delete that because I now have got an expression for the temperature of coffee. And I'm going to connect it like this, and then I'm going to move it around because I do not like spaghetti code. And these blocks out here, I want to make them the same size, because you want to make blocks of the same type, generally the same size. It's just good practice. So if you right click, go to arrange, and then match size, and then I want to center them, so right click again, arrange, and align center. Okay, now remember that I have not used this value of 70 degrees Celsius anywhere. So where would that get used? So mathematically, when we integrate, what do we get? We get a constant of integration, right? So that is basically our initial value. So that's the initial value for the temperature of coffee. So double click, and in our initial condition, I'm going to type 70. Now pull out a scope so that we can see the temperature of coffee, and then press the run button. Okay, so the good news is it's running, but it's only ran for 10 seconds. So let's go back here and run it for say 20 minutes. So that's 1200 seconds. Okay, so we still have not reached steady state, but see that the temperature of coffee is dropping and reaching room temperature. So let's just run this for say an hour and see what we get. Great, so the thermal inertia has equilibrated with the room temperature and has reached room temperature at about 2500 seconds. And that's how we run simulations in Simulink. The last topic I want to talk about is configuration parameters. For that, go to modeling and then click on model settings. So out here you will see that you got a lot of different settings, right? Simulation time, solver selection, solver details. Now what I would recommend is, if you're not sure what you need, don't be concerned with this, that's what I would say. But there are a couple of things that I would like to talk about. Okay, so solver type. So there are different kinds of continuous time solvers out here, and there is a discrete time solver. Again, if you're not sure which one you need, I would just leave it at automatic for the time being. When it comes to solver, or when it comes to the type, whether you're at variable step or fixed step. So first of all, what is this? So remember when I said that Simulink executes repeatedly for the complete simulation time? Well, then the question would be, how frequently does it execute, right? And then why would you need to necessarily have this happening at a fixed frequency or a variable frequency? So a fixed step basically means that if I choose a fixed step along with a fixed step size, it means, let's say in this case it's 1 second, or else I could use 0.1 seconds. So if I use a fixed step of 0.1 seconds, it means that the complete simulation is going to be executing at 0.1 seconds for 3600 seconds. With a variable step, Simulink is going to automatically evaluate what is the right rate for execution. And you might ask why? Well, it actually saves on simulation time sometimes. So if a simulation has reached a steady state, then a variable step solver will just reduce how frequently the system executes. I like doing most of my work with a fixed step because that way I feel that I'm in better control of my work. And I'm going to use a fixed step size of 1 second, press OK, save, run. Well, and you obviously, just get a very similar result. So those were the basics of running in Simulink. I'm going to be posting a few more videos on Simulink. Please smash the like and subscribe button so that they show up on your feed. If you have any feedback or specific questions on Simulink, please leave a comment below. Thanks.